We've seen earlier that there is a way to calculate the percentage of carbon, hydrogen, and oxygen by use of a combustion chamber, which has some copper oxide pellets, which actually supplies a little bit of the oxygen while the sample is burning, and then two different traps, one of which is a water trap, and then the other one is a carbon dioxide trap. And then using the masses of those before and after, we can figure out how much carbon, hydrogen, and oxygen are present in the original sample. In the example that we're given, we start with a 4.24 milligram sample of acetic acid. Okay, this acetic acid is completely burned in a combustion chamber, and we get 6.21 milligrams carbon dioxide and 2.54 milligrams of water. We are asked to find the mass percentage. So the question is, what is the mass percent of each element? So here's what we're going to do. We're first going to convert the mass. So step number one, we'll convert the mass of carbon dioxide to moles. Okay? Then what we'll notice is that we can convert this to moles of carbon, noting that 1 mole of carbon produces 1 mole of carbon dioxide. So 1 mole carbon produces 1 mole of carbon dioxide. And lastly, you would convert to mass. So we're going to convert from mass of carbon dioxide to moles of carbon dioxide. We know through stoichiometry that 1 mole of carbon is 1 mole of carbon dioxide. So then we will convert from moles of C to mass, or grams of C, or milligrams of C, depending on what it is that you're working with. In a similar method, or a similar fashion, we're going to convert the mass of water. So convert mass of water to moles. And then we'll convert to moles of hydrogen. Okay, so let's give this a shot. We're going to start out with our 6.21 times 10 to the minus 3 grams, which is 6.21 milligrams of carbon dioxide. We're going to need the molar mass of carbon dioxide. So 1 mole of CO2 is 44.0 grams of carbon dioxide. Okay. So this will convert grams of carbon dioxide to moles of carbon dioxide. And we said that 1 mole of carbon produces 1 mole of carbon dioxide. So we'll go ahead and lastly convert from moles of carbon into grams of carbon. So we need the molar mass of just regular old carbon, so 12.0 grams over 1 mole. When we do this calculation, we end up getting 1.69 times 10 to the minus 3 grams of carbon, or in other words, 1.69 milligrams of carbon. Okay? So we've successfully converted from the mass of the carbon dioxide to moles of carbon dioxide, to moles of carbon, and then from moles of carbon to the mass of carbon. So there we have that. So for the hydrogen, we'll always start with what we know, we have 2.54 times 10 to the minus 3 grams, which is 2.54 milligrams of water. So grams of H2O. We're going to convert that into moles. So 1 mole of water weighs approximately 18 grams. Okay, so there's a molar mass. We know that 2 moles of hydrogen are produced for every 1 mole of water. H2O, right? Okay? And then lastly, we would just need to convert from moles into mass of hydrogen. So 1.01 grams over 1 mole. Running out of room. When we actually perform that calculation, we end up getting 2.85 times 10 to the minus 4 grams of hydrogen, which is 0.285 milligrams of hydrogen. Okay? So now we have the mass of carbon and the mass of hydrogen in the original sample. So let's go ahead and find the mass percentage of each one of these. We'll start with carbon. So the mass percent of carbon is the part divided by the whole, or 1.69 milligrams divided by the original sample, the weight of the original sample, 4.24 milligrams, multiplied by 100%, and we get 39.9% carbon. Similarly, we can do the same thing with the mass of hydrogen. So mass percent of hydrogen. We take the weight of hydrogen, 0.285 milligrams, and divide it by the original weight of the sample, 4.24 milligrams, times 100%. And we should get 6.72% hydrogen. Now, what we can do is we can use these percentages to figure out the mass of oxygen in the original sample, because we know that the two of these added together have to be 100%. So, 39.9% plus 6.72% plus some other number, which is going to be the percent of oxygen, have to equal 100%. Solving for x, we should have a mass percent of oxygen equal to 53.4%. And once again, this is how we calculate the mass percent given a combustion reaction.